Alright, what we're going to be talking about today is changes of state and how to calculate how much heat it takes to change the state of an object. And by state, I mean one of three things: solid, liquid, and gas. So if you want to go from a solid to liquid, so going this way, solid to liquid, that's called melting. Going from liquid to gas, that's called evaporating or boiling. And then going back, going from a liquid to a gas, gas to a liquid, we call that condensing. And then we go from liquid to solid, that's freezing. So how much energy does it take to change the state of an object? Solid, liquid, and gas. And believe it or not, there are actually two more states of matter that we don't talk about but do exist in nature. So if you get hotter, you melt stuff. If you get hotter still, you get a gas. If you make gas so hot the electrons just wander away from it, we call it a plasma. The fourth state. And then there's something even colder. So if you cool plasma, you get gas. If you cool glass, you get a liquid. If you cool liquid, you get a solid. If you cool a solid even further, you get something that's called a Bose-Einstein condensate. Sometimes abbreviated to BEC. So that's something weird that we talk about in quantum mechanics, because literally what happens is, imagine I get these two pens cold, they actually overlap one another. They can take up the same place at the same time. They're like ghosts, where you can get things of really weird density. They just overflow one another. But that's a discussion for another day. But just know that there are 5 states of matter right now in physics. So how much energy does it take to change the state of an object? What I'm going to do, I'm looking at page 323. And you see this graph right here. In this graph, you'll see and this is heat down here in joules, and this is temperature. Now, the first day of class, we melted snow. And we actually saw a little bit of this graph. We saw this spot right here. We started with snow and we ended with boiling water. So this temperature right here is 0 degrees Celsius, and this temperature right here is 100 degrees Celsius. Now, a really common question. How much heat does it take to boil off water at room temperature? So let's say room temperature is 23 degrees Celsius. So you might think to yourself, oh, all I got to do is heat it up. So like, how much heat does it take to heat water? Well, let's say I've got 1 kilogram. No, let's say I got 2 kilograms just for argument's sake, because one might. So my mass is 2, the specific heat of water is 4180, and I'm going from 23 all the way up to 100. So I'm changing temperature 100 minus 23. So if you run that through on your calculator, you end up with 644,000 joules, or 644 kilojoules. A lot of people think, hey, that's how much energy it takes to boil off water. You'd be in fact wrong, because check this out. This is my phase diagram. I'm starting with water right here. That water is 23 degrees. This 644 kilojoules, that's how much energy it takes to make the water boil. So this energy is the energy it takes to heat water. Now, I have not boiled the water off. Literally, I've raised the temperature to 100 degrees. Now what I have to do is boil off the water, and this takes a new equation. When you're boiling something off, you use the equation Q equals the mass times the heat of vaporization. HV stands for how much energy it takes to boil something off. Just like there's another equation for when you're working down here. If you want to melt something or freeze it, we'd use the equation Q equals mH of F, heat of fusion. So the H of F stands for heat of fusion. It's how much heat to melt / freeze 1 kilogram of a substance. HV stands for heat of vaporization. That stands for how much heat to boil / condense 1 kilogram of a substance. So here's where we're going to use this. Back to my question, how much heat does it take to boil off water at room temperature? Well, we've figured out how much water it takes, how much heat it takes to raise the temperature. Now I have to figure out how much heat it takes to boil it off. So this is my second phase. So this is step 1, heat it up. Step 2, boil it off. Step 1, heat it up. Step 2, boil off. So now I'm going to use Q equals mH of V. So my mass, assuming I don't lose anything, my mass is still 2. And you have to look up the heat of vaporization for steam. And that can be found on page 324. So the heat of vaporization for steam is 2.26 times 10 to the 6. So we'll multiply that together, you get 4.52 E6, or 4,520,000 joules. So now I have to add these, and you got to be careful. This one's in kilojoules. I could also write this as 4,520 kilojoules. So I can add 644 plus 4,520. And I get 5164. So the total heat equals 5164 kilojoules, or 5.164 megajoules, or 5,164,000 joules. That's how much heat it takes to boil off water at room temperature. Now, what if the question asked, what if you started with ice? Well, there's an example problem number 3 in your book. Example problem number 3 on page 325 says, suppose you are camping in the mountains. You need to melt 1.5 kilograms of snow at 0 degrees Celsius, and you want to heat it to make hot cocoa. How much heat is needed? So in this problem, you're starting with snow, so you're starting here, and you want to make hot cocoa, which is there. It's 70 degree water. So this stuff right here is ice. This stuff right here is water. This stuff right here is steam. Now this is just for water, by the way. This works for everything, like copper, mercury. I mean, you name anything, you can make it solid, you could make it liquid, you could make it a gas, depending upon what temperature you're at. If you're at the boiling point or the freezing point. So in example 3, you're starting here. First of all, it's a two-step problem. You have to first melt all of the ice. So you take the mass times the heat of fusion for ice. And then you have to heat the water, mc delta T. So let's give this one a try. So in this problem, step 1 is going to be heat the snow. And by heating, I actually mean melting the snow. So I'm going to go mH of F. So the mass of the snow is 1.50. This is example number 3 on page 325. The mass 1.50, the heat of fusion for snow 3.34 times 10 to the 5th. So I multiply those two numbers and I get 501,000. So that's how much it took to heat the snow. Step 2 is going to be heat the water. So I use Q equals mc delta T. My mass hasn't changed. The specific heat of water is 4180. And now I'm going up to 70 degrees from 0. That's the final temperature minus the initial. So if I take 1.5 times 4180 times 70, I get 439,000. Now how much heat does it take in total? I have to add these two numbers together. So 439,000 plus 501,000, I get 940,000 joules. This is how much energy it takes to melt snow and then make hot cocoa. These are phase changes. So first of all, I have to melt the snow and then I have to heat the snow. Melting the snow, heating the snow. Now, you can get really, really nasty problems too that are literally 5 steps long. Like, what if I had ice at negative 20 degrees Celsius and I wanted to change that into superheated steam at a positive 200 degrees Celsius. So this problem, going from cold ice to hot steam, this is a 5-step problem. You're starting here with really cold ice. First you must heat the ice to its melting point. Then you've got to melt the ice. And then you've got to heat the water to its boiling point. And then you've got to boil everything off. And then you've got to heat the steam till your superheated state. So this is literally going to be a 5-step problem. So first of all, I'm going to heat the ice. So it would be mc delta T. The next step, I'm going to melt the ice. That's the heat of fusion. And then I'm going to heat the water. And then I'm going to melt the water, or I'm sorry, boil it off. And then I'm going to lastly heat the steam. Now it's interesting, the specific heat is different. This is for ice, water, steam. Those can be found on page 319. Heats of fusion, heats of vaporization for ice and for steam. Those can also be found on page 324. So this has been changing the states of objects from to solid to liquid to gas, and how you can figure out how much energy it takes to do that.